Hello, this is Mr. Wynn, and this video is solving systems of inequalities in linear programming or optimization. So to solve a system of inequalities, you simply graph each inequality on a coordinate plane and find the overlap shading. That section is called the feasible region. The steps are very simple. Again, you graph each inequality in shade, and you check if there's an overlap. If yes, that overlap area is the answer on the graph. And if no overlap, then you say no solution. Make sure you can graph constant lines. Those are just vertical or horizontal. It's horizontal if y equals a number. It's vertical if x equals a number. Make sure you remember our AHK transformations, the vertical stretch, vertical compress, left, right, up, down stuff. And make sure you use the cover method if it's in standard form for linear. So here's the first problem. Solve some inequalities. Now we have one letter and a number that's a constant. So this is constant, this is x equals 5. So I'll find 5 on the number line. I'll say 5 is about right here. And it's vertical and it's dotted. So this is basically x is always 5, because if I said this point here, that's 5, 0. This is like 5, 1, 5, 2, 5, 3, and so on, because x is always 5. Doesn't matter y. Now to do shading, I still use a test point for shading, so I'll try 0, 0 as my test point. I plug in 0, 0. 0 is less than 5. That is true. So I shade this side 0, 0, meaning the left side. So I'll shade over here. Alright, so there's the first picture. The same thing for the second one. This is y is equal to 10. So that's a constant line. Again, it's a horizontal. I find 10 on the y-axis. 10 is somewhere over here. Let's call this 10. Sideways line, and it's closed. Nice to do shading. So I still like 0, 0. That's below the line. 0 for y. There's no x plugin. 0 is less or greater than 10. That's false. Since shade setting the bottom side with 0, 0, I'll shade the top side. Alright, so I look, there's an overlap, and there is. It's this box or rectangle right here. All of this is the answer. That's the feasible region, the top left of the graph. And that's it. The answer is the graph. Alright, here's another one. Solve the system of inequalities. These are no longer constant lines, but I can use my HK. I know this is linear. It's a diagonal line. It's not vertically stretched or compressed because A is 1. There's no left or right because there's no parentheses, but that is up 7. And this is solid. So from 0, 0, I go up 7. Let's call this 7 right here. And I draw a diagonal line that is solid. There's no stretch or compress. It should be exactly 45 degrees. I do shading. So let's plug in 0, 0 as a test point. 0 is greater than or equal to 0 plus 7. 0 is bigger than or equal to 7. That's false. So I avoid the 0, 0 side. I shade over here. Alright, I do the same thing for the line. Again, linear. It's AHK form. So it's linear, it's a diagonal line. There's no A, so no vertical stretch or compress, no left or right, but that is down 5. And this one is dotted. So from 0, 0, down 5, let's call this 5. 0, negative 5. I draw a diagonal line dotted, and it's not stretch compressed, so it's perfect 45 degree angle. If you notice, these lines are parallel. I said do shading, test point. Let's try 0, 0 again. 0 is less than 0 minus 5. 0 is less than negative 5. That's false, so I avoid the 0, 0 side. I shade the bottom side. So I check, is there any overlap? The answer to that is no. So this is no solution. Because there's no overlap. Alright, there might be more than 2 inequalities, and there's just 3 of them. So solve each, so we're going to graph each and see there's an overlap. So here it has to be a triple overlap area. The first one, that's standard form, I do cover-up method. So I do 2x equals 6, 3y equals 6. That makes x equals 3 for the coordinate 3, 0. This is y equals 2. When I divide 3, I get the coordinate 0, 2. And this line is solid. So let's put those on here. Let's say 3, 0 is somewhere over here. And 0, 2 is somewhere over here. Connected solid line. Shading, let's do a test point. Let's pick 0, 0. 0 plus 0 is greater than or equal to 6. 0 is bigger than 6. That is false. So I avoid the 0, 0 side. I shade this other side. All right, the second one, it is linear. Diagonal line. It is vertically stretched. It is down 10. And this is dotted. So 0, 0, down 10. Let's call this 10. Linear line, vertically stretched and dotted. All right, pick a test point. Let's pick 0, 0. 0 is greater than 0 minus 10. 0 is bigger than negative 10. That is true. Should I say the 0, 0 side? Alright, if you can tell, it's like an X right now. The top of the X is where it's both green and red. That's the overlap so far. Let's try another one. This last one's constant. That's, alright, this is constant. It's y equals, so it's actually sideways. So I'm going to go 7 for y. If that's 2, 7's above there. Cut 0, 7. And it's solid. So sideways line. I pick a test point. I like 0, 0. 0 is less than or equal to 7. That is true. So I shade down here. Alright, kind of messy picture, but there is an overlap. It's a little triangle. So it's above this red line right here, below this blue line right there, and above this green line right here. So this right here, this area is our feasible region. Any point in that area is a solution. Alright, be able to answer for points of solution or not. Is 1, 4 solution to the following system of inequalities? You could graph the whole thing and see if the point is obviously inside the feasible region, but that takes too long, so we can do what we always do, plug it in, treat it like a test point. But instead of just one equation, you have to plug in all the equations. It has to make all the equations true. If it is, it's a solution. If it makes even one false, you stop and say, no, it's not. So I'll plug in 1, 4 here. 1's x, this is y. So it's 4 less than 5. Yeah, that's true, that's good. Now I try the other one. So let's do, all right, y is 4. That's equal to 1 minus 2 plus 3. 4 stays there. I work on the inside. That's a negative 1. Once you have a single number inside the absolute value sign, it comes out as a positive 1 plus 3. You put parentheses if you want, but 4 is less than or equal to 4. Well, 4 is equal to 4, and that counts. That's true. Since both of them are true, it is a solution. So yes, solution. Now you could graph this. Not hard. So let me just graph it real fast. This one is a constant. It's sideways. So y at 5 and it's dotted. I'll show you that's not really helpful. So this is, let's call this 5. Sideways line. Dotted. If I do test point 0, 0, is 0 less than 5? Yeah. So I shade down here. Try this other one. That is absolute value. It's a V shape. It is right 2, up 3, solid. So from 0, 0, I'm going to go right 2, up 3. That's 5. 3 somewhere over here. So let's call it a 2, comma 3. Draw a V. I'm not stretching and compressing it, and it's solid. I can pick test point 0, 0. I'll plug it in. 0 going to equal to 0 minus 2 plus 3. Inside is negative 2. Comes out positive 2 in parentheses. That 0 is 5. That's false. So instead of shading where the 0, 0 side, I'll shade inside this. I'll do it like this. All right. There is an overlap. The overlap is right here. Now, can we tell if 1, 4 is in there? Again, our picture's not drawn to scale, so not really. You should just plug in and be safe. All right, that is solving system inequalities. Now we have what we call linear programming. It's related, similar. Linear programming is a method for finding the maximum and minimum values of a function. It's commonly used for efficiency in real life when you have constraints, such as minimizing costs, maximizing profits, or minimizing waste, maximizing space and storage. The steps, you're going to graph each inequality and shade. You find the overlap, shading the feasible region. Now, when there's a shape, you have to find the vertices of the feasible region. So right here, I'd have to find what, let me put in red, what this point is, what this point is, what this point is. All right, those points are special. You can plug each vertex into the end, some end equation, some final equation, and you'll find the greatest or least result. So here's what I mean. And to make it easy, here's the finished problem. So each week, Mackenzie can make 10 to 25 necklaces, 15 to 40 pairs of earrings. If she earns profits of $3 on each pair of earrings and $5 on each necklace, she plans to sell all at least 30. How can she maximize her profit? Well, she has a lot of restrictions. She can make 10 to 25 necklaces. So my equation is necklaces has to be more than 10. So here's the n axis, but here's n greater than 10. If you look at this, it's then she has to make at least so 10, or she can do this up to 25, which is over here. It's n less than or equal to 25. But it's between these two, so that's why we have this rectangle right here for now, and I'll erase that later. Then she has the next condition, 15 to 40 earrings. So earrings has to be greater than or equal to 15, also less than or equal to 40. Here's my e-axis. So this line right here is e. Yeah, that's 15. Good. We're going to go 15. And then here's the e less than or equal to 40. All right, but it has to be between those two. That's why we have this. So right now, just focus on the overlap is this box. Then we have another equation. She must sell at least 30 pieces of jewelry. So I'll say x plus y has to be greater than or equal to 30. If I do the cover-up method there, I get x equals 30, y equals 30. So those are the points 30, 0, and 0, 30. Now, one's off screen, but here's 0, 30. And off screen over here somewhere, I'll say is 30, 0. You can see it's connected, dotted. But if I do test point 0, 0, I get 0 is greater than or equal to 30. That's false. So I shade above. So now that this rectangle turned into this shape. Make it blue. So here's the rectangle, but it got cut right here. And then it goes up to this. That's our feasible region. That's all the overlaps. So we need the 5 points. There's one right here, vertices, 3, 4, 5. Those are the ones that matter. All right, so now let me erase all these marks so you can see the picture better. So again, we're looking here. Any point in here will make her conditions met, true. But we want to find the maximum and minimum results. So I'm going to pick one of those points and plug into some n equation. The n equation happens to be our profit equation right here. So again, she earns $5 for every necklace and $3 for every earring. If I pick 10, 40, I plug it in, I do 5 times 10 plus 3 times 40 for a profit. Well, that's 50 plus 120. That gives me 170. That's where this number comes from. All right, now, is that the highest? Maybe. I'm going to plug in a different point. By plugging all these points, that's what this box down here is, you can see all the different numbers. She makes $110 for one situation, which makes 10 and 20. That's the minimum. She makes 120 from making 15. She makes 170 by making 25 necklaces, 15 earrings. Or if she does her maximum limit, she makes the full number of necklaces and earrings, 25 and 40, she'll make $245. That is her most profit. That's the maximum. All right, and 110 right here, that is the minimum. All right, any point inside that shaded area will always be between that 110 and 245 because that's the minimum and maximum. Now to make your life easier, I'm not going to make you graph this whole thing. I'll give you something like this, where I give you the picture already, it has the shaded area, and I give you the points. All you got to do is plug it in. So here's what's going to look like. All right, so once you plug in those 3 points, the x and y to the equation, if I plug in 520, I get negative 85. That's the lowest, so that's my minimum. And then you get 60 for the point and 450 for the last one. 450 is my maximum. All right, so again, on your test, I'll give you a picture where you have this. You just plug in the x, y points into the equation, see what's the highest and lowest number, and that's it. Hope to see you in class. Again, ask questions in class. See you soon. Bye.